In this lesson, we will define the Legendre symbol that will help us determine quadratic residues mod of prime, and we will look at the law of quadratic reciprocity. So the Legendre symbol looks like an integer over an odd prime p with parentheses around it. And we'll define this in a minute, but I just want to point out that the Legendre symbol greatly simplifies quadratic residue computations. So we're still looking at the question of how can you determine if A is a quadratic residue mod P? In other words, how can we tell if the congruence x squared congruent to A mod P is solvable? We have Euler's criterion, which helps us determine when A is a quadratic residue, but the Legendre symbol is actually even easier to compute. So let's define the Legendre symbol. So the Legendre symbol, A over P, for an odd prime P, is defined as A over P will equal 1 if A is a quadratic residue mod P, the Legendre symbol A over P will equal 0 if P divides A, or so equivalently if A is 0 mod P, and the Legendre symbol equals -1 if A is a quadratic non-residue. Mod P. We begin with a theorem which gives some properties of the Legendre symbol, and these are the properties that will help us determine quadratic residues mod an odd prime P. So let me state these properties as a theorem. So let P be an odd prime the first property of the Legendre symbol says that if A is congruent to B mod P, then the Legendre symbol A over P is equal to B over P. Secondly, the second property, if A is not congruent to 0 mod P, then the Legendre symbol A over P is congruent to A to the power P minus 1 over 2 mod P. Thirdly, if A times B is not congruent to 0 mod P, then A B over P equals A over P times B over P. Fourth property, -1 over P equals -1 to the power P minus 1 over 2. So this property says that -1 is a quadratic residue of P if P is congruent to 1 mod 4, because then you'll get -1 to an even power. But if P is congruent to 3 mod 4, then -1 to an odd power will be -1, and therefore -1 is a quadratic non-residue. The fifth property, if A is not congruent to 0 mod P, then A squared over P will always equal 1. And the sixth property, 2 over P equals -1 to the P squared minus 1 over 8 power. Another way of restating is that 2 will be a quadratic residue mod P if P is plus or minus 1 mod 8, and 2 is a quadratic non-residue mod P if P is congruent to plus or minus 3 mod 8. These properties of the Legendre symbol, combined with one more, which we'll discuss later, the law of quadratic reciprocity, make the calculations fairly simple to determine if A is a quadratic residue mod a prime, odd prime P. Now we give the proof of these properties. Let's begin with the proof of property 1. So recall property 1 says if A and B are congruent mod P, then A over P is equal to B over P. Well, if A and B are both 0 mod P, then the Legendre symbols will both equal 0. So if A is congruent to B, and they're both not congruent to 0 mod P, then we see that x squared congruent to A mod P is solvable. Then clearly x squared congruent to B mod P is solvable. So x squared congruent to A mod P is solvable if and only if x squared congruent to B mod P is solvable. So therefore, the Legendre symbols A over P and B over P must be equal. Let's get the proof of property 2. So if A is not congruent to 0 mod P, then A over P is congruent to A to the power P minus 1 over 2 mod P. If you think about it, this is just a restatement of Euler's criterion. Using the Legendre symbol. Because we know that A to the P minus 1 over 2 will be congruent to 1 mod P if A is a quadratic residue, and it will equal -1 otherwise. 3 is a very useful multiplicative property of the Legendre symbol. So if A times B is not congruent to 0 mod P, then by property 2, I can write AB over P as the quantity AB to the power P minus 1 over 2. So these two quantities are congruent. But I can distribute this exponent to write this as A to the P minus 1 over 2 times B to the P minus 1 over 2. And again, using property 2, these are congruent to A over P and B over P mod P. So look at this chain of congruences. So AB over P is congruent to A over P times B over P mod P. But the quantities on the left end and the right end of this congruence have to equal plus or minus 1. If they have to equal plus or minus 1 and they're both congruent, and they are congruent mod an odd prime P, they have to be equal. If one side is 1, then the other side has to be congruent to 1 or equal to 1. And likewise with negative 1. So since the left end and the right end are plus 1 or minus 1, and they are congruent, mod the odd prime P, they must be equal. So this establishes the multiplicative property of the Legendre symbol. Next, the proof of property 4. Well, again, we're going to use property 2. By property 2, negative 1 over P, the Legendre symbol, is congruent to negative 1. Just plugging in negative 1 for A in property 2. Negative 1 to the P minus 1 over 2 mod P. So again, since negative 1 over P has to equal plus or minus 1, and negative 1 to the P minus 1 over 2 is equal to plus or minus 1, we see as similar to the last property that since they're both congruent mod and odd prime P, they must be equal. So since the left and right sides are plus 1 or minus 1, and they're congruent mod the odd prime P, they must be equal. So now for property 5, which states that A squared over P is equal to 1 when A is not 0 mod P. We start out with A squared over P, then by property 3, we can break this up as A over P times A over P. Then I can write this as A over P, the quantity squared, and so whether or not A over P is 1 or minus 1, when I square it, I will get 1. So if there's a square in the top of the Legendre symbol, then that's squared over P will always be equal to 1. Now property 6 is much more involved, but it's very useful. So let's see the proof of property 6. We're going to consider some congruences. Consider the following P minus 1 over 2 congruences. I'm going to start out with P minus 1, and that is congruent to negative 1 mod P, but I'm going to write it as 1 times negative 1 to the power 1 mod P. Then the number 2 is congruent to 2 mod P, but I'm going to write it as 2 times negative 1 squared mod P. Then the next congruence will be P minus 3. And you see the pattern. I'm going to write this as 3 times negative 1 cubed mod P, because P minus 3 is congruent to negative 3, and negative 3 is equivalent to 3 times negative 1 cubed. Then I have 4. We're going to alternate back and forth between these types of expressions. So 4 is congruent to 4 to the power 4 times negative 1 to the power 4. So the last congruence will be r congruent to p minus 1 over 2 times negative 1 to the p minus 1 over 2 power mod p. And I'm not sure whether r is going to look like p minus an integer or an even integer. So r is either, or r equals, is going to equal p minus 1 over 2 if p is 1 mod 4, or r will be p minus p minus 1 over 2 if p is congruent to 3 mod 4. Okay, so we have a total of p minus 1 over 2 congruences. Now I'm going to multiply these congruences together. So multiplying these together gives the congruence. On the left hand side, we have all the factors, all the even factors from 2 up to p minus 1. So it's going to look like 2 times 4 times 6 up to p minus 1. And on the right hand side, we get 1 times 2 times, we have factors of 1, 2, 3, and 4 all the way up to p minus 1 over 2. So I'm going to write those first factors as p minus 1 over 2 factorial. And then I have a bunch of factors of negative 1. So I have negative 1 to the first power, 1 plus 2 plus 3, all the way up to p minus 1 over 2. So I'm going to combine all those factors of negative 1, mod p. If I look at the left-hand side, each of the factors on the left-hand side has a factor of 2. So if I pull out the factors of 2, I'll end up with p minus 1 over 2 factors of 2. So I can rewrite the left-hand side as 2 to the power p minus 1 over 2 by factoring out all of the factors of 2 on the left-hand side. And what I'm left with is 1 times 2 times 3 all the way up to p minus 1 over 2, which I'm going to rewrite as p minus 1 over 2 factorial. And we notice that factor is in common on both sides of this congruence, so we'll deal with that next. So we can divide or cancel the factor of p minus 1 over 2 factorial because this is a product of numbers that are not 0 mod p. So since none of the factors are congruent to 0 mod p, this whole factorial is not congruent to 0 mod p. To obtain, so now we have on the left hand side 2 to the power p minus 1 over 2, and on the right hand side this is congruent to negative 1 to the power 1 plus 2 plus 3 up to p minus 1 over 2. And there's a classic formula for the sum of the first n integers. The sum of the first n integers would be n times n plus 1 over 2. So if I use that formula, 1 plus 2 plus 3 up to p minus 1 over 2 would equal p minus 1 over 2 times, if I add 1 to this, I get p plus 1 over 2. It's the same as adding 2 over 2. And then I have to divide this whole thing by 2. So it'd be n times n plus 1 over 2. So I'm going to write that as times 1/2. And when I expand this expression, we see that this just equals p squared minus 1 over 8. And that's the exponent we need in the formula for property 6. So we have, let me just wrap this up. And if you notice that the left-hand side, 2 to the power p minus 1 over 2, well, that's congruent to the Legendre symbol 2 over p. So, and by 2, the Legendre symbol 2 over p is equal to 2 to the power p minus 1 over 2. Thus, the Legendre symbol 2 over p is congruent to negative 1 to the power p squared minus 1 over 8. So this is mod p. And since the left-hand side and the right-hand side are both equal to plus or minus 1, we must have that the Legendre symbol 2 over p is actually equal to negative 1 to the power p squared minus 1 over 8. So again, since the left and right sides are plus or minus 1, and they're congruent mod the odd prime p, they must be equal. So this establishes the proof of property 6. So now let's look at a quick example of how these properties will simplify our calculations for quadratic residues. So suppose I wanted to determine if negative 360 is a quadratic residue mod p. Then to do that, we could evaluate the Legendre symbol negative 360 over p. Now if I look at the prime factorization of negative 360, let me take out the factor of negative 1, and then I see that this is equal to 2 cubed times 3 squared times 5. And we know that anytime you have a squared factor like 3 squared, when I break up the Legendre symbol using the multiplicative property 3 squared over p will just equal 1. So we can always remove any even powers of a prime factor. So example 2 cubed, I can think of that as 2 squared times 2, so that will simplify as well. And so I have a 2 squared and a 3 squared, which is equal to 36. So when I break up the Legendre symbol, I'm going to break it up as negative 1 over p, and then we have a factor of 36. So that's good to always, if you have a Legendre symbol where the top is a perfect square, that will always be congruent to 1. That will always be equal to 1. So this part is 1. Also a factor of 10 over p. So if I break up the Legendre symbol this way, we see that this is going to be equal to the Legendre symbol negative 1 over p, and 36 over p is just 1, so then I could just have 10 over p, but I can break that up as 2 times 5, so this is 2 over p times 5 over p. So think about our properties. We know how to evaluate negative 1 over p. We know how to evaluate 2 over p. We have formulas for that. The only thing we don't have a formula for is a Legendre symbol like the last one, 5 over p. So it turns out if we can figure out how to evaluate negative 1 over p, 2 over p, and then an odd prime q over an odd prime p, then we can completely determine Legendre symbols, even with very large integers. So in general, we can evaluate the Legendre symbol A over P if we can evaluate the Legendre symbols negative 1 over P, 2 over P, and Q over P, where Q is not prime. It turns out that the last symbol, Q over P, can be evaluated with the help of a very fundamental theorem of number theory called the law of quadratic reciprocity. And we'll present this theorem next. So we can evaluate Q over P with help from the following theorem. So this theorem is a very important theorem in the history of number theory. It's called the law of quadratic reciprocity. So this theorem was conjectured in the mid-1700s, but was proved first by Gauss in 1796 after he worked for a whole year, and he was at the ripe old age of 19 when he gave this first proof, and he gave 8 proofs in all during his lifetime. And this was one of his most proudest achievements, is proving this law of quadratic reciprocity. So this is first proved by Gauss in 1796. So the law of quadratic reciprocity relates the Legendre symbols P over Q and Q over P, where P and Q are distinct positive odd primes. So the law says if P and Q are distinct odd primes, it's distinct positive odd primes, then the Legendre symbol P over Q equals Q over P when P is congruent to 1 mod 4, or if Q is congruent to 1 mod 4. If it happens that P and Q are both congruent to 3 mod 4, then the Legendre symbol P over Q will be equal to the negative of Q over P. So this occurs when P and Q are both congruent to 3 mod 4. So we can actually combine these two statements and write this more briefly as P over Q times Q over P will be equal to negative 1 to the power p minus 1 over 2 times q minus 1 over 2. So as I mentioned, Gauss first proved this theorem in 1796, and it took him a whole year of his life to come up with a proof. So the proof, as you may guess, is quite involved, and so I'm not going to present the proof of this theorem. However, if you want to see the proof, you can look in Levecque's book on pages 101 through 105. So the proof, again, is very in-depth, and we'll actually use this theorem without presenting its proof, because the proof would take up pretty much a whole lecture, and so we're just going to assume that it's true, and it is true, and we're going to use it without actually demonstrating the proof ourselves. I will offer some history of this theorem. So the law of quadratic reciprocity was first conjectured by Euler in the 1740s, and Legendre also formulated this theorem in the 1780s. They both tried to prove this theorem and were unsuccessful. They both gave incomplete proofs in the year 1785. Several years later, Gauss actually discovered this theorem on his own. He was apparently unaware of the previous work of Euler and Legendre, and he worked for a whole year before completing the proof in 1796 at the age of 19. Gauss, in his writings, referred to this theorem as the fundamental theorem, and in his whole lifetime he gave 8 proofs, 6 while he was alive, and then 2 were found in his papers after he died. And as Levecque states in his book on page 108, he says that this theorem has proved to be of the highest importance throughout a large portion of number theory. Besides being a powerful tool for solving problems, it has been a fruitful source of new problems. So there's over 200 known proofs of this theorem, and through efforts to prove this theorem, completely new branches of mathematics and new techniques and new problems were created as a way to attack this theorem. And Levecque also notes that Gauss initiated the study of algebraic number theory while trying to prove this theorem. And currently, in June 2014, there are at least 246 known proofs of the law of quadratic reciprocity. So let's see the power of this theorem in action. Suppose I wanted to determine if a number was a quadratic residue mod 5. So for example, is x squared congruent to 3 mod 5 solvable? Or is 3 a quadratic residue mod 5? Well, oftentimes when we start out with examples, we use relatively small numbers just to kind of motivate the theory or the problem at hand. But we don't need all this machinery to evaluate to figure this question out. We could just examine a complete residue system mod 5. But you can find some very, very large primes. So even with, for example, 4-digit primes, computing this by looking at a complete residue system mod p would be just too time consuming. So that's when you see the power of the Legendre symbols. So let's make this question a little bit harder. So is x squared congruent to 3,437 mod 5,473 solvable? Well, to answer this question, we will evaluate the Legendre symbol 3,437 over 5,473. So just as a note, 5,473 is prime and moreover it's congruent to 1 mod 4. That's useful. So 5,473 is 1 more than a multiple of 4. So 3,437 factors as 7 times 491. So by law 3, I can rewrite this as 7 times 7 over 5,473 times 491 over 5,473. Well, now we can use the law of quadratic reciprocity to flip these Legendre symbols, because 7 and 491 are both prime, and since 5,473 is 1 mod 4, I can flip these Legendre symbols, and I don't have to put in a minus sign. So when I flip them, they'll both be equal. And now I'm going to reduce 5,473 mod the second entry. This is property 1. So 5,473 is actually congruent to 6 mod 7. And 5,473 is 72 mod 491. So I can replace the Legendre symbols with these, 6 over 7 and 72 over 491. Now by property 3, I can factor 6 as 2 times 3, so this is 2 over 7 times 3 over 7. And 72, I'm going to factor this as 36 over 491, because 36 is a perfect square, and then I have 2 over 491. So we know that 36 over 491 is going to be 1, and 2 over 7 is going to be equal to 1, because 7 is negative 1 mod 8. So by properties 6 and 5, I can write 2 over 7 as 1, and then I still have 3 over 7, and 36 over 491 is 1 by property 5, because 36 is 6 squared, and then I have 2 over 491. I can evaluate that, and that's going to equal negative 1, because by property 6, 491 is 3 mod 8. So far I have this Legendre symbol is the negative of 3 over 7. Let's use the law of quadratic reciprocity again. 3 and 7 are both 3 mod 4. So when I flip the Legendre symbol, 7 over 3, I have to take the negative of it, because by the law of quadratic reciprocity. So we just get positive the Legendre symbol of 7 over 3. By property 1, I can reduce 7 mod 3, and this is the Legendre symbol 1 over 3, but 1 is a perfect square, 1 is 1 squared, so this will equal 1. So what I've just shown, that the Legendre symbol 3,437 over 5,473 is equal to 1. Therefore, x squared congruent to 3,437 mod 5,473 is solvable.